Hey, John here. Let's talk about Verilog vectors and arrays, what the differences are and how you use them.
As always, thank you. Thank you to all my Patreons, especially the VIPs. You really help out. Thank you again. You want to get involved in the fun, head on over to patreon.com. There'll be a link in the description below this video on YouTube. And if you want to just, chat about the videos, come up with ideas, let me know what I do wrong. There's a nice Discord that started with the Z80 Retro project and is bleeding over into this, so we'll just use the same one. It's fine. Head on over there. Let me know what you think. A lot of good people there. Today, let's look at these four new directories, types. We're looking at data types today, specifically vectors and arrays. Verilog treats the two very differently. Let's make sure we understand what's going on. Let's make sure I know what to talk about. So the first example, the README file, I'm going to talk about a vector. All right, and these are what you and I might think of as a regular latch or something. If you don't know anything about Verilog, and you might know something about soldering in some chips and whatnot, the vector is your multi-bit bus, maybe a data bus. I shouldn't say latch because that infers other ideas and things. We're not quite there yet, but in this context, this is sort of like the address bus or a data bus. You got an 8-bit data bus or a 16-bit address bus on the good old 8-bit microprocessor days, okay? We're also going to talk about the concatenation operator. You'll see when we put things inside curly braces, what we're going to do is we're going to just take all the bits from multiple signals or buses and concatenate them together into one big wider set of bits. And that's what we're going to do with this. We got big and little bit ordering that we'll see when we define a range of bits, when you define a wire or a reg data type. There's this bit range in here, and you can either go from low to high numbers for your indices, or you can go from high to low numbers, okay? It's sort of like big endian and little endian, but at the bit level. So let's look at our sample test bench example code. Okay, so what do we got? The first comment in the file: Verilog treats vectors as a binary integer with regard to the fact that Verilog knows how to dump them out. And we'll look at the display when we're formatting multi-bit vectors in binary, hex, decimal, and even octal. Okay, so what do we got here? We got a couple of reg data types, and the reason these are regs and not wires is because we're going to assign a value to them in an initial block, which we can't do if they're wires, right? So how do you define a vector? Well, you put your data type here, in this case it's reg, you give it a range of bits. These are the numeric indices that you're going to use to access the various bits in your vector. You can, as I mentioned before, you can do it the other way around. But this is backwards in my opinion. All right, let me know if you think this is the better way to go. Other than, IBM mainframes is the only machine I ever used. And I suppose there are some TI DSPs that work this way, where the big, most significant bit was in the 0th bit position, which is strange to me because I've always thought of the most significant bit as being in the largest numbered bit position. And if you use it this way, what happens is the significance of each one of these 4 bits in the range of 0 to 3 represents a magnitude, when you interpret the value as a binary integer, of 2 to the 0th power for the least significant bit column, 2 to the 1 power for the next bit column, and so on. And those numbers match these array indices. All right? This is how most systems that I've ever used work. So this, in spite of the fact that I don't like to have to put the big number first when I type in my code, this is actually more natural for me anyway. All right? Both ways will work. and it helps if you're consistent. Well, I've done some inconsistent stuff in this file. We'll see what happens when you screw this up. As you go, you get very confused. Whatever you do, pick one way and stay with it. Okay. All right, the usual here. We have an initial block that we're going to use to just run a bunch of sequential code with a bunch of delays in here. So we can look at it if we want to plot it. We got a bunch of displays that we can look at on the screen with just text printouts when we run this code. So what are we going to do? We're going to dump all these variables to a file so that we can plot it. We want to see what's in the v vector, the v variable, the v reg, before we do anything, okay? And you'll see it'll print it out in decimal. In this case, it has no value yet, so it'll be unknown, and this will print out an unknown value. We can also print it out in binary like this, okay? And then we're going to wait. What are we going to do? We're going to set it to 1. We're going to set the least significant bit of v to a 1, print it out. Then we're going to set the whole vector at once can be set if we want to 0, or you can set the whole vector to 7 or something like that. We'll see that in another example later on. When you have a vector, because Verilog treats it as a binary integer, I can assign the value 7 to the whole thing, and it'll unravel it and convert it to binary and assign it that way if that's what you want. So you can do that, which is handy, right? So where do we leave off? I can set 1 bit, and that's how you index a single bit. That's how you set the whole thing in one fell swoop. And default, this is decimal. We'll talk about other types in a minute. You can set the most significant bit if you want. And then what we got? We got a B. So this is the backwards one. Let's just look at the first part of this example, and then we'll move on to the second one there. Okay, so let's compile it, and this will run it. So remember, the first thing I did is print out V with a display to print it all out in the default way, which would be a decimal value of the whole thing. It's unknown because it was never set, so it prints out X. The next thing I did was to print it out in binary. Not yet set because there's a delay down here before it gets set down there. That one will also print out unknown, but it'll do it in binary. So each individual bit is unknown. We know the length is 4. It goes from 3 down to 0. For those of you that are VHDL fans, you actually define vectors in VHDL using, literally you say down to 0 when you define them. The next thing I do, I set the least significant bit to a 1 and dump it out again. Notice that these are lowercase x's, and this is an uppercase x. What happens is a lowercase x is printed out when all the bits, 100% of whatever you printed out, okay, if it's a single bit, then it's a single bit. But if I print all 4 of them out at once as a decimal value, if all 4 are unknown, you get a lowercase x. If any of them are known, you get a capital X if you're printing out a group of bits at a time. So this is decimal, and this is, oh no, this is hex. Clearly that's hex, and decimal is over here. And you can see it's an uppercase X because when I printed it out in binary, I had 3 unknowns, and the least significant bit was a 1, which was because I did this. Okay, so this is how you mess around with these bits. Very next thing I do is set the whole lot to 0. Then I set the most significant bit to a 1. And I did the most significant bit on purpose because if we look at this, while Verilog treats that as a binary number, right now, this is an unsigned binary number. Because if it was signed, that would be, what, a -7. And yet it prints out an 8 in hex. That's correct, because hex is hex. It doesn't have sign. I suppose you could have a signed hex value, but normally you don't print out hex values with negative signs and stuff like that. Decimal, however, would be signed with a minus in front of it if this was to be taken as a negative value. And we'll see that in a minute as we move forward. You know that the next thing I did here, what was that? Okay, so I got The least significant bit, I set the whole thing to 0 and print it out. Set the most significant bit to a 1, I print it out, I got an 8. So I guess I set it back to 0 again in the code for whatever reason. There's the most significant bit. This time I'm messing around with array B. And I do this on purpose because remember A was little endian and array B is big endian. If you look closely, if you didn't notice yet, that says 3:0 and this one says 0:3. This one's backwards. Even though, like I said before, I feel this is more natural for me to type in a bit range in a declaration like this, a definition like that. But this is this is the way you want to do it. Okay, so let's see what we got here. B is 0. B0 is set to a 1, and B2 is set to a 1, and I print it out as I go. All right. Remember that B0 is the most significant bit. Probably would have been a good idea for me to skip a blank line before I do this. This is me printing out B when I set it to 0. This is me setting B0 to a 1. Now B0 is on the left, okay? Because I set 0 to 3 instead of 3 to 0. When I set A0 to a 1, I got the 1 on the right, all right? So get this straight in your head. This could be very weird if you ever mix them up. This was, I set B2 to a 1 and then printed it out. So that's this bit right there because this is B0, B1, B2. It is not B1 and B2 from the other side, okay? This here is B3. Then what do? It looks like I'm printing out the same thing twice. So I set the B2 to 1. I assign V the value of B. So what the heck is going on here? I'm copying a big endian value in the B reg to a little endian value in the V reg. So let's look and see what happens when the binary is printed out. Let me add that blank line that was eluding us earlier so that we can make sure we're all looking at the right line. All I'm going to do here is just say display with nothing. That should print me a nice blank line. I'll do another one down here before I get creative with the screwed up flippy-floppying of the copyings. So here's me printing out B0, or rather the B thing after I set it to 0. Here's me setting the most significant bit and B sub 2 right there. Then there's a blank line. And now I assign V the value from B. Notice that I'm printing out the same value here. When I copy from B to V, it does bits one at a time in order from most significant to least significant. It does what one might consider the right thing when I copied that value over to V, okay? So I said V equals B and printed it out. And now I still get the same bits in the same order visually when you print them out from most significant to least significant in left to right order. In other words, the display here, when it prints out the bits, it will print them out in most significant to least significant order regardless of how we ordered the bits in our vector. And when we do the assignment, the same thing takes place. Okay? In other words, V sub 0 did not get assigned the value from B sub 0. Here's how you do that if you really want to. All right? So there's our V equals B. I should do something like this. Put a marker in here like that to let us know that's this one. So now this one down here, let's look and see the concatenation operator in action. We'll see this in a second down here, but if I wanted to, I could specify a range of bits, and that's how you would do it, but the problem is B is big endian. If I try to do this, let's go ahead and compile it. I'll show you what happens. It's going to gripe, at least I hope so. Yes, it does. It says, look, I want to select part of B, in this case all of it, but a portion of B, in this from 3 to 0, but that's out of order. Okay, and it says during elaboration. That's during the compilation process. Okay, so this one can't even compile because the bits are out of order. If you really wanted them out of order, in other words, if you wanted V sub 0 to equal B sub 0, all right, you do it like this. Or if you want to be explicit, you can also go like that. This should also work perfectly fine. Yes, it does. Okay, so this is probably more illustrative of what's going on so you realize what's happening. So V, in order from 3 down to 0, is now going to be B3, B2, B1, and B0. But remember that B0 is the most significant bit, and this is the least significant bit. So these now are definitely backwards. So if you did a 1-to-1 based on these index numbers, and you copied a vector from one to the other, and flipped it around, forcibly flipped it around, and then printed it out, this is what you would get. Notice this one is the one that comes after the new V equals B message in here. Okay, so there's the V equals B message. And when I flipped it around the other way, I get a 5. And of course, now I've ruined my alignment. Let me do this. This is probably what I should have done. I call my new boss the alignment king because when we write our code, he is very sensitive to alignments and stuff, and with good reason. You know, it's much easier to read your output. So now it jumps out at me when I have something that's not aligned nice. Anyhow, here's the V equals B, and it copies them straight through in most significant to least significant order, I would say logically, right? Here's when I did it one at a time, and I made V0 equals B0, so that's this thing equals the one from over there. This one, B1 or V1 equals B1, gets that one there. V2 here gets B2 there, and so on, all right? So that's why you get the bits flipped out of the in reverse order. And that's how you would do it. You'd use a concatenation operator. And like I said before, you just put something in curly braces, put commas between each one of the items. Okay? This so happens to be that each one of those items are bits. You could use bit ranges in here and whole vectors if you wanted to. And it'll just concatenate them all together and make that assignment to your left-hand side over here, all right? So that's what happened with that one. Then what am I doing? Here is now, what do? I put a 0 in the V and waste a time period for no reason. Then I set a bit range in the correct order. Since V is little endian, I want to set the range of 3 to 2. And I want to put the decimal value 3 in there. Now, you got to think a lot about in your head what you're doing here, right? Oops, I'm going to delete that whole line. That'll make it even harder to understand. So remember that 3 in decimal equals 1, 1 in binary. And what I'm going to do is I'm going to add in the next example, what happens, oops, yeah, this is a decimal number. When you say single quote D like that, you're saying decimal. That's Verilog's way of saying, how do I want to express this? And if I get a single quote B, that's binary. So you can simply say that decimal 3, and this is Verilog's way of doing that, equals a binary 1, 1. So what I've done is I've set the two most significant bits to 1s. And then I printed it out, and then I'm done. So let's go ahead and run this one. And there you have the 3, the 2 1s right there. In hex it's C, and in decimal that's 12. Okay, if you don't know what's going on, sit down, draw a diagram. Draw this up with 4 spaces on a piece of graph paper if you have to. I'm taking this value and sticking it into a bit range in the middle of, potentially, of some other vector. That's what's happening here. Okay, this is very common. Although I'm not sure I would literally do this in my code, put a decimal value in it. Maybe, but it's very common to grab ranges, in other words, of vectors in Verilog, okay? Let's look at the second example. What do we got going on here? We got vectors. We got a replication operator. Look at the difference between that and the concatenation. All right. In a replication, what we're going to see is you got an open curly. It looks like we're going to do a catenation. However, the first thing that's going to be in the replication is a number that says, here's how many times I want to repeat this value here. And it's a little wonky, in my opinion, because you can't put like a comma here and keep going and combine the replication with the catenation. No, this is literally what this thing is supposed to look like. All right, so we'll see one of those. What are we going to? The sized integers. Now, before I was talking about based integers. Okay, when you say single quote and then you put a base in here and then you put a value, that's what Verilog refers to as a based integer. What number base am I using? We can also use a sized integer. Now this is a markdown file, so these backwards quotes are really the markdown. It's to let GitHub know not to format this and use these single quotes in any weird ways. So ignore these backwards jobbies in this particular context. In fact, we should be able to go over to the website. We should be able to go over to the website here and see what it's supposed to look like. If we go over here and look at the markdown, all nice and presentable like. So see how these are all in the highlighted gray. That's the point, all right? So a sized integer has a number and a quote and then a value. A based is just a quote, a base, and a value, which I just showed you before, okay? You can combine these two and say, here's a number, a sized integer, and the size refers to how many bits. So I want a 9-bit value. So you'd say 9 quote, and then you put a number in there, 7 or something like that, right? But I can also say 9 quote B for binary, 101, and put 9 bits of binary over there if I want to. We're going to have a look-see at this. This will sign extend a number, a la 2's complement, and we'll see that plus and minus. Verilog knows how to create an adder circuit, which is absolutely wonderful because it's not uncommon to need to add and subtract things when you're building these machines. And because it knows about them, it knows about that fast carry chain that all FPGAs have them, so that it will actually use those and create a more efficient circuit when you're trying to add and subtract. All right, so what does this example look like? What do we got here? We got a couple of vectors, just like before. Now I got a 16-bit vector and a 32-bit vector. Vector of 16-bit. Yeah, it looks like I cut and pasted something. I should have updated this because that was wrong. Now it's correct. I'll go ahead and add a similar comment here. This one's a vector of 32 bits. When you're just getting started, the last thing you need is some doofus to give you the wrong documentation. And subtle things like this drives me nuts. Because you don't have any way of knowing that the person's lying. Right? Okay, so I got two vectors here. One's got 16, one's got 32 bits. These are little endian. Okay. The usual thing, dumps the stuff. In the previous example, I didn't really need to do that, but it might be neat to look at these in waveforms if we want, and that's what we do this for. And we'll see there's another reason I'm going to talk about the dump file in these particular examples in a future example. So keeping them in my face and reminding us all how this works is a good idea, because it's going to change when we get to arrays. Okay, so what do we got here? We got a V and a V32. What am I going to do? I'm going to print out the garbage value with all the unknowns. It'll print an X, right? Then I'm just going to print it out when I got all zeros in there. I'm going to set it equal to a -1, and I'm going to print it out. I'm now going to use an unsized but based value. This is in decimal. I could just as easily make it in hex with an H there, because a 2 in hex is also a 2 in decimal, right? I'm not going to leave it changed because then my doc would be wrong. All right, so let's run this first one. So 1, 2, 3, the first 4 displays, and this one prints it out twice. We see this sign extension going on here. So let's look closely at this. Let's put a blank line in here before it so it's easy to find. And I'll push all this after I record this so that we're all looking at the same code. Oh, look at all this down here. We'll get there soon enough. What do we got? We print out the thing before we set it to any value. We get the X that we're used to seeing. Here's the 0 after I set it to 0. When I printed it out after I set it to a -1, I got 65535, which anybody who knows 8-bit micros knows that's FFFF in hex, all ones in binary, and 17777 in octal. I'm not an octal guy. I threw it in there in case we got some octal people out there. Octal works out fairly well on the 8080 and the Z80 because they have 3-bit groupings of various fields, which, if you go back and look at something like the Altair S100 system, the switches that control the front panel were in 3s, and therefore a lot of people used octal when they programmed their Z80s. I never knew what octal was. I learned hex first before I knew of octal, and I just stuck with it. And most systems today use hex. These are useful when you're grouping your bits into 3s. I'm just saying, right? So anyway, that's your -1 expressed in decimal in an unsigned interpretation of a 16-bit binary number with all ones, okay? So that's why this printed out a -1. We skip a line. I set it to a -2, and I print it out again. Let's skip another line after that. And what do we got going on here? See, I say signed, all right? So I print out exactly like I did up here. Let's scroll back up a little bit. I set it to a -1. I print the V out in its entirety in the default, which will be decimal, right? Then I said print out decimal, hex, binary, octal. Now I set it to -2 just to get interesting. And I'm going to print out decimal, hex, binary, and octal again. Then I'm going to use this $sign thing. Now what this says is to take this value and treat it as a 2's complement signed binary value and extend it to the number of bits needed to be interpreted that way by this $display system task, okay? So let's see what happens here. Remember, I did this, skipped a line, and set it to -2, and then I printed it out as V, and now I'm printing it out as $signed V. This is the only field that changes. It changes in length, too. Notice it's all moved over one. Why? Because there needs to be room for the minus sign. And in case it printed out the maximum value, which would have the same number of digits as this, it would need that extra space in order to print the negative value out. So that's why these are shifted over one, and all these are all printed out in unsigned and signed variants, as we'll see. So that's why these are all jaggy like this, okay? I'm going to say I did that on purpose so that I remember to mention that there's an extra character in there to hold the sign. So, -1 looks like this in binary, -2 looks like that. We all know that. If you don't, go grab a nice Wikipedia page on 2's complement binary numbers and make sure you follow along. FFFE is -2 in hex and so on, okay? So, this works. So you can put a signed, unsized, there's no length here before the single quote, and we specify a base of decimal whose value is 2. All right, here's a hex one. I'm going to say this one is unsized in hex whose value is FC0. And I'm going to print it out again, both unsigned and signed. After the last time I skipped a blank line, and that's this one, obviously the OFCO. And it's because that's a positive value. It's going to print it out the same way both times, and it's going to reserve space for the sign, even though we have a plus and it doesn't print the plus. So then what happens after that one? I'm going to print a hex 8000. Okay. This is the most significant bit being set, and because V has 16 bits in it, it is literally the most significant bit of V will be on, and that's the signed bit if you are familiar with your 2's complements, right? So we should see the in the hex, the X here, it should print 8000 and 8000 again here, and then the decimal one here should print a negative of the value, should be interpreted as a negative number, and this one up here will be interpreted as positive. That's halfway to 64K, which you round it off to 32K, which would be 32768. We know it's an even number because it ends with a 0. Okay, so it's not 32767. It must be 32768. I get those kind of confused. This one down here, the negative value, would be 32768 as well, because it too has its least significant bit set to a 0. Binary, you can clearly see right there. Okay, so this is the positive, the unsigned interpretation, and the signed interpretation. Okay. What do we got going down here? What comes after the 8000? Now I set V32. Remember, this is the 32-bit vector in a little endian order. The exact same thing, except it just has more bits. Okay. I say V32 equals V. And because I didn't sign extend it, like we'll see down here, Verilog will 0 extend it for me. In other words, it'll take all the bits that are in V. It'll add as many more that are needed to be added on the left side, the most significant side, and then it'll assign that total grouping of bits to V32. And then I print it out in the usual way like this, do a delay, and then let's play around down there. Let's put another blank line after this guy. So we don't get lost. So that was this one right here, right? What was I doing here? Right before the display, yes. So this is the 0 extended assignment to the larger vector. So when I print this out, even though the format string's the same, it should print these all out as 32-bit values instead of 16-bit values, right? And that's what's happening. So this value here is 32 bits in hex, 32 bits in binary, 32 bits in octal, and it's the 32-bit 0 extended up here, oops, on the left, copy of this. So this is V, and this is V32 after we assign V to V32, right? So I cannot stress enough that this is 0 extended on the left, okay? Now, let's say I don't want that, and I want it sign extended, all right? I can extend it myself. Now, this is the replication operator. This is really ugly and messy, which is one of the reasons you can just use $sign and let the compiler do it. This is a little more obvious of your intention. So I suggest strongly, if you mean to sign extend a value, do it like this. This is only here for purpose of demonstration, for us to understand what you would, let's say you didn't know of this, right? Or you had some other reason you wanted to replicate some field into multiple bits or extract some other thing out, right? How do you do that? Notice there's our curly braces within which there is this number followed by an inside set of curly braces. Maybe if I remove these spaces, it'll be visually more obvious that these are kind of bound together like that, okay? Now you can see that, you've got the outer curlies and then there's the inner ones inside here, okay? And there's the number that says, here's how many times I want to replicate what's in here. Now make sure you listen to that very closely. This is not the number of bits. 24, in this case, there's only one bit in here, so we will get 24 bits. But that's not what the 24 means. The 24 means I want 24 copies of what is in here. So if I then say follow this by, let's say, a 2-bit hexadecimal value of 2. Now what I got now is 24 times 3 total bits, because this is 1 bit here, concatenated with 2 bits over there. So what does that come to? 24 of these plus 48 of those is, what, 72 bits total for this, okay, which is much bigger than my target, so this is weird anyway. But I wanted you to understand that what's inside these inner parentheses can be any multi-bit value that will be repeated, that in this case 24 times. All right, so this is the example. If you want to manually sign extend it, you take the most significant bit of your vector and repeat it as many times as needed to fill out the total width to your target, which is your 32, right? So actually it's not 24. It should be 16. It turns out it's okay, because if I do it too many times, it'll throw away the stuff on the left. So if this is 16 or more, it'll do what you want it to do. I put 24 in there because originally V had 8. And moving on, all right? This is a good example anyway, because the compiler will silently let that go and truncate the result and stick it in the target. So this is what's going on here. You can clearly see this is sign extended. Takes the most significant bit of V, which is a 1. You can see it in here, or most easily right there. And then it repeats it 16 times here in binary, or 16 times there in binary as viewed by hex octal again. And the value in decimal is this giant thing here. Okay? Now, just to show you that I wasn't malarkeying you, if we lose one of these bits, now what's going to happen? I don't have enough bits. So what it's going to do now is take the 16 out of here, 15 here, almost sign extending it all the way, leaving a 0 on the far left, and leaving you with a positive value. So there you go, all right? So that's just me making sure that this time I got the right number of bits, okay? Look over your shoulder. Okay, so 16 times with the sign extension works fine. I strongly suggest you go through and play with these examples and tinker with them just like I did right here to see what would really happen. Just for fun, why don't we even do this, right? We know in this particular example that the most significant bit is a 1. So let's go ahead and do a 1-bit binary value of 0 in there. So now what I'm going to get is 16 1, 0 pairs. Okay? I better. Okay, so there's your 16 times the 10101010, right? And in hex, that's your A. Okay? So, all right, just a little having fun here. Okay, 16 of those works. And, of course, we ended up with too many bits. And, yes, it threw away the most significant ones when we had 16 times 2 bits coming out of here, as opposed to now when you only have 16 times 1 bits. Okay, so that's when we printed out this guy here. Now we're going to print it out with $signed. Now that I'm done screwing around with this, we have the proper sign extension, and we're printing it out here, which is unsigned with a giant 4 billion number. And then down here we'll print out the signed value, which should be a relatively small negative value. Yes, 32768 makes a lot of sense because that's what we assigned it in the first place. All right, or negative rather. Okay, so what is the point here? The point is, while display can treat it as a 2's complement signed binary number, we have to be careful what we give to display so that the value is the right number of bits and the type is known so that it knows to make it to print it out as a negative value if that's what your intention is. Now we can also do this, and we can sign extend the V like I said before. Let's put another blank line in here. And now we have a signed extended V without all the malarkey up there. And we should see the same exact thing without the malarkey down here. Yada, yada, yada. 528, FFFF 8000, binary and decimal, and octal rather. This line here and this line here are the exact same thing, because asking it to sign extend it for us works, right? Now notice that even though I said signed, when I assigned it to the V32, the display still prints it out as a positive number. It's because it's still just a bunch of bits, and it doesn't yet know it's supposed to be signed unless I use the signed system task here to make it so. All right. And I put a note here, note the extra width. When I do that, what's happening is, notice this thing shifted to the right one. So what it did here is, I was talking about that before. This here, it was printing it out as an unsigned value. Here's a signed value that could be as many digits as that and need to have a sign on the left. So you'll see it takes up more space. Okay? That's what that comment was about. Now we got what? Verilog knows how to synthesize an adder. Woo-hoo-hoo! This is really nice. Otherwise, you'd have to create an entire addition circuit in order to add numbers and create all your little full adders and deal with all the carries and all that fun stuff. Thank you, Verilog. You can just simply say, hey, V32 is V32 plus 12, or you can say plus equal 12. Okay, in this case, it's doing both of these. I'll add, 24 to the V32 value. I'll print it out again with the signed system task in there, and I will see that one run. So that's this down here. Is that correct? Yes, I printed it out only once with the sign extended thing after the last time I printed a blank line, and that is this line right here. So this should be 32768 plus 24, which looks good to me in decimal. And in hex, here it is plus 24. 24 in hex is 18, which makes sense because 10 in hex is 16 and 8 is 8. Therefore, 16 plus 8 is 24. And in binary, here you see, and in octal as well. Okay, so we can add, and it understands 2's complement, therefore you get subtraction for free. And if you haven't been noticing, that's one of the reasons we use 2's complement. Adding and subtracting in binary when you're using 2's complement numbers is basically the same operation. Just you do a 2's complement. You invert all the bits. We can build a circuit to do that later. If you're interested, let me know in the notes below, or Google it, work it out on paper. This is why we use 2's complement, people. The gates and circuitry are vastly simplified. 1's complement, try it sometime. Try adding 4 to -2, okay? And see if you can use the same circuit as you do when you add 4 to a +2. It's a little annoying having 2 separate values for 0 is the spoiler of that little story. Okay, so moving on. We can add and subtract because Verilog knows how to create adders on the fly, on demand, even in synthesized code. It's a wonderful thing. So we can then print that out. And what do we do now? We can also negate the value like that if we want to and print it out one last time. Let's see what we got here. So this, what did I say? Minus 20,000 or 200,000. That makes sense because you see the 2 pop in right there. Then I negate the value and print it out again. So this is negative 23, blah, 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 blah. And here's positive 23, blah, 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 blah. And in binary, you can sort of see the relationship between these 2 values. All right? And octal. Okay, so what's the takeaway here? replication operator, how you do sizing and how you use different number bases, how you assign extend things and get display to tell you whether your value has a negative sign in front of it or not, and how you can do addition and subtraction. Oops. Let's see what we got next here. What are we doing here? First time I saw an array in Verilog. Very confusing. So, I cannot stress enough, these are not the same thing at all. They work very differently. We're also going to see a for loop and the integer data type, okay? The array, notice the ranges are on the right of the variable. Remember that the vector, this range of bits, was on the left. So when you're first getting going with this, there's a little bit of a subtlety. Let's take another look at that. The previous example here. These said reg, or you can do this with a wire as well. You can say here's the range of the bit numbers in your vector that is called V. And I never think of it this way, but I've been told that if you read these from right to left, and when you teach C and C++, I learned it without knowing this rule, which does make sense in retrospect, but it's been decades, so I'm stuck in the way that I do it. But I'll point this out in case it helps you. What you're doing here is you're looking at a thing called V that is a range of bits of type reg. Okay? And when you look at that in contrast to an array, now we have an array called A that is a range of bits that's not specified, and therefore it's a single bit of type reg. Okay? So arrays are over here. And these work like they do in C, C++, Java, .NET, and all the other languages you may be familiar with if you tinker around writing code. Okay? This is a multi-dimensional array. So this is an array called A that has, what has it got? An array of 4 bits. There's 4 elements that are each 1-bit registers. Here's an array, or rather I should say it's an array of arrays of bits called B, okay? And there's 4 arrays of 4 arrays of bits, okay? Now I have an integer in here because you're going to see a for loop down below, and for loops are interesting beasts in Verilog because they're not like you think they are in like a C program. But they make it handy when you're printing out a 2-dimensional array, so you don't have to write in many, many lines of code. We'll touch on the for loop for now and put a pin in that. We'll come back to it a little bit later when we talk about what happens if you put a for loop in your Verilog program when you're creating synthesized code. How in the world does hardware execute a for loop? Okay, for now, I'm going to just wave my hands and say we're using it in a simulation. And in a simulation, it works like we're all familiar with. Okay? But in order to create an index, you create an index of type integer, just to keep the newcomers on their toes and introduce a new data type. Now is when the dump vars get screwy. We've got what? Before I said just put dump vars in there like this, it'll dump everything and it's all fine and dandy. And it's great, unless you have an array. Now, by default, dump vars on its own will not dump arrays. If you want an array dumped, you got to specifically say which arrays you want dumped. Probably this is so that they don't create these colossally gigantic files. There's a lot of threads on the internet when I see people griping about this. We're using Icarus to do our simulation, and some people are asking, how come I can't just put a flag in here or say dump all the array vars or something like that, and there's all this dialogue back and forth. Yes, no, we got to do it. We can't do it. Honestly, when you get a discussion like that, I personally get peeved off, especially when I want it to dump my arrays, like today. And the people are defending it and giving all kinds of foolish reasons. Look, if I'm stupid enough to dump all my arrays and create a 5 terabyte file, that's on me. Not on you, okay? By not providing a simple way to do this, you're making my life difficult. And for what reason? Because you're helping me not waste my disk space? I sigh in tiredness here. Okay, so anyway, moving on. If you want to dump your arrays, you got to name every stinking one of them. And because, whoa, I'm not in Vim here. Let's open it in an editor. And because each one of these things needs to be dumped out on its own, I got to name them all. I couldn't say A, it won't do them all. And I couldn't even do B, it won't do them all. I don't, maybe not, I don't know. What does it do if I do that? No. Whatever. We'll come back to it. If I'm wrong, tell me in the notes below. I always do it like this. I hardly ever use arrays, by the way, in my Verilog code. I do when I have to generate some complicated thing, and we'll see generate loops and all that stuff. I want to introduce it now, but I don't usually dump them out, so it's, you know, on the one hand, I think they should have a decent way to do this. On the other hand, you don't really need to do it anyway. So, moving on. Okay. What am I going to do? First of all, I cannot set every one of the elements in an array all at once to 0, like I can in a vector. Okay? Now, one of the reasons you can't do this is because Verilog thinks of an array like it's a memory. Remember, an FPGA, quite often, all FPGAs I know of, have embedded block RAMs inside of them. And you put an address into it, and then it has a data bus and stuff like that. How many RAMs, static RAMs, do you know where you can set every bit in the entire RAM all at once? They're not made that way, and neither are the block RAMs inside your FPGA. So if you really think about it, this is something really wonky. And while the simulator could do that, this is certainly not anything that could ever be synthesized in a sane manner. Okay, this is just not allowed. Okay, you don't set a whole range of bytes in your RAM on your machine to 7 and have the hardware do it all in one cycle. No, that's not how that works. And because it thinks of these as memory blocks, that's what this is asking to do, and it won't work. It won't compile. Okay, so what do? We wait a little bit. We set the, A0. I almost said least significant bit, but that's not what we're doing here. We're setting element number 0, which happens to be a bit, to 1. Then we're going to display the 4 bits. Let's play our game with our blank line, and we'll move down our blank line as we go to keep our position. Okay, what do we got here? Here's the first one when we set the 1, and the rest of them are all unknown. This is a warning that you're going to get. Go ahead and Google it. Welcome to the debate on why you can't dump out an array all in one wad and what this is all about. I don't normally do this, so I never really looked into all the details. I believe this has to do with how the simulator names all the variables when you've got a hierarchical design. This is something that's better understood later. For now, just accept the fact that this warning comes out and it's okay. Okay? And we'll move on for now. Okay, so the first time we did this, we put the element number 0 set to 1, and the rest were all unset. That's why we've got this. Okay. Then I'm going to move this thing down and put it right there. So now what are we going to do? We're going to set A1 equals 0, and then we're going to dump them out again, and that will all make sense, right? If I set A0 to a 1, and I print out all 4, and they before now were all unknown, I would get 1 XXX. This should give me a 1 0 double X, which is right there. Works perfectly. This down here is a hexadecimal A, but we're doing it 1 bit at a time. So what do we got here? I'm going to just keep moving that down, and that's actually down here already. So what are we doing? 2 and 3 are 1 and 0. So we got starting from the left, we got a 1, 0, 1, 1. From left to right like this, and that's what I believe we saw in the last run. We got a 1 0 1 0. Now I don't know what's on with that. What's happening down here? So we're going to leave that one alone. Now I'm going to set array B. Okay, now I have a 2-dimensional array, and this one's harder to print out. I mean, I suppose I could have just replicated this line 4 times, but you should know what a for loop does and how it works anyway. It works just like it does in C, except you can't use a plus plus operator, which is a bit of a drag. I'm constantly typing these things in wrong and then going out and fixing it after I get an error. But, okay, so what's happening here? I set B00 to a 1. Then I go through and print out all 4 elements of my array, all 4, you can think of it as rows, right? So I'm thinking about these as rows and these as columns, I guess, right? Which way am I doing this? I think I did that backwards, but yeah, so the first dimension I'm using as the row number, and the second dimension I'm using as the column, all right? So I'm going to just print them out. So I set 0, 0 to a 1 and print them all out. Then I set 0, 1 to a 1, print them out, and a 1, 2 to a 1, I print that out. So let's see what we got. What I got? 00, 01, 1, 2. So we should see an 00 in the upper left, 01 and a 1, 2. And that makes sense because 0, 0, in my view, is upper left corner. And then you go down this way, row 0, row 1, row 2, and so on. Column 0, 1, 2, 3, like that. Okay? So this is how you define an array. You cannot print out an array. Like if you try, you'll get an error like this. So you have to iterate through it and go and do the whole thing. It says, I cannot support an argument type something or other memory. So there's a clue there that Verilog thinks of A as a memory, and B would even be worse because this is a 2-dimensional one, right? So that's just not allowed. We can, because I did dump vars like this, we'll see the A array elements in the dump log, but the B won't be there. So if I say make plot, it should open up the plotter and the thing will run. Here we go. I can click this. You see everything that's in the top level module. Oops, I can hit Control A, click on append, and I can see all these values here. And as you recall, A was unset, and then slowly I set them one at a time to these various values. Okay? And nowhere to be found in the VCD file was the B array. Oops. All right, let's look at types 4. Now we have the crown jewel. I have an array of 4 elements called AA, each of which is a vector of 4 bits of type reg. This is an array of vectors. And this is the thing that got me a little head twisted the first time I tried to do one of these. So, watch closely. Because these are vectors, and vectors are understandable to Verilog as a multi-bit numeric value. If I do a dump vars on AA0, that's okay. Because this is not a 2-dimensional array. This is a 1-dimensional array of vectors. And dump vars will save vectors. So I just saved a vector called AA0, a vector called AA1, and so on. All right? And again, we'll get this warning, but it's going to be okay. Now, I cannot set all of them at once because I'm assigning a value to multiple vectors all at once. All the elements of this array cannot be set at once. We just saw that in the previous example. However, if I go to AA0, and I should probably keep this up here on the screen so we got it for reference. AA0 is the zeroth element of an array whose type is a vector. So there's nothing wrong with me assigning the decimal value 12 to a vector of 4 bits, and that's what that means. Then I dump out all 4 values and go on my merry way. Then I set 03 to a 0. Whoa! What's going on here? Well, now this represents the bit in the vector that I'm setting to 0. Let's look closely at these two lines. And then skip a line right there. So to make sure that I got the right bits, notice that 12 changed into a 4. Why didn't I do this in binary? This is foolishness, I tell you. Let's go ahead and leave that in there, and then let's add a %b. Nope. Yeah, of just AA0. I don't want to mess with the other ones in this particular case, because we're only messing with AA0. Okay, so these are going to come out in pairs. So we'll be able to see the binary value. You know what? We can actually do this all on one line. Why not? This is really wonky, but you can do this, okay? Display is a variadic function that will apply this format to as many items in this list that match the number of formatted things. Then it will just continue on and dump the rest out as it normally does. This is not intuitive to a C programmer. Wow, okay? But that's what this is going to do. So let's go ahead and learn something. Okay, what do we got? Here's my binary. Here's my decimal. Let's put a space in there. The alignment king is going to get upset with me. All right, here we go. 4 bits in binary. 12 is a 1100. A 4 is a 100. Of course it is, right? But why did it do this? How did this happen? What was going on? Notice these are all lowercase x's. Therefore, none of these 4-bit vectors have any of their bits set to any known value. Otherwise, you'd see a capital X in there, right? Okay, so I set vector number 0 to a binary value of 12, which is, what is it, 1100. In hex, that would be a C. Down here, I said, go to 03 and set that bit to a 0. This is the most significant bit of element 0. And because we now see it in binary, we can clearly see that we're looking at the right one. I made this think about the x's because I wanted to make sure that I know that when I said 0 and 3, I meant the most significant bit of a 0, the first element, not the least significant bit of the last vector in that array, okay? So this is proof that I did it right, okay? Make sure you understand the order in which those things are supposed to appear. I skip a blank line. What do we got now? A2 will appear as an uppercase X, just like I was talking about. So now if we do this, we'll see a capital X pop up for double A2. I didn't even notice that in the previous run. Yes, it's right here, okay? So by poking at one of the 4 bits in element number 2, right, because this is A0, A1, A2, then you'll see an uppercase X in there. If I then set the other 3 bits one at a time, nothing wrong with that, and print out again, I should see a value that I recognize in there. Why did I do it in such a wonky order? That's number 2, 0, 1, and 3. So that 0 and 1 are 1s, and 2 and 3 are 0. That should be a 3 in AA2. Yes, and there's my 3 right there. Okay, so that's what I wanted to go over today. These multi-bit values of vectors and arrays, and what happens with sign extension, how you concatenate bits, and how you can replicate fields, and how you can write a for loop in order to display your data like I showed you in this example here, so that you don't have to type your brains out every time you're trying to display some data. So let me know what you think in the comments below on YouTube. Thanks for watching. I'll see you next time.